So last time we saw the definition of a limit, and before we defined limits, we had to define cluster points. So I've just copied down the definition of cluster point. Um, a cluster point of a set is a point that we can get close to. Okay, we can get close to without being at that point. Okay. So in this definition, as we saw kind of last time, the set A is usually, we're thinking about that as the domain of our function, and the point C is where we'd like to take a limit. Okay? So, I will copy it down one more time. The definition of a limit. So, let C be a cluster point of the set A in R, and suppose F maps from A to R. Okay, so A is the domain of this function F, and C is a point that we can approach from within A. Then we say the real number L is a limit, although we did prove last time, or we talked about the proof, that limits are unique, so we could use the word the there, really. It's the limit of F at C if, and now we have to remember our quantifiers, okay? For every epsilon, okay, that's how close we want to get to the limit L. For every epsilon, there is a delta. That's how close we get to our point C in the domain, such that for all x that are in A but not equal to C, if x is within delta of C, then f of x is within epsilon of L. Okay. Most important features of this definition are really the end. If you can keep your quantifiers straight, remembering that is probably going to be enough. What do we want? We want the function to be close to the limit within epsilon. What are we allowed to control? How close we go to the point C. But we absolutely do not care what the function is at the point C. That's why we're not allowing x to be equal to C. Okay? So we don't care at all what the function is there. Okay. Any questions with the definition before we go on?
I have a quick question.
Mm-hmm.
So if we think of this like a game for proving, we want to set a condition on the distance between x and c to force the function to be close to L.
Yeah, so if we think about it as a game, our opponent picks the epsilon, then we get to pick the delta. Okay? And then we pick a delta, and then the following statement has to be true for all x. Okay? Now, I usually don't recommend this, but I'll make an exception this time. It's sort of, if we look at the quantifiers here, what are they? For all epsilon, there exists a delta such that for all x in A minus C, the following holds, and the following is an implication. Okay, so logically it's slightly complicated, right? For all there exists for all implication. Okay. We actually already worked through the negation of this. There exists an epsilon such that no matter how you choose delta, there is always an x that satisfies the conditions that such that f of x minus L is not less than epsilon. Okay, now the first thing we obviously have to do is an example or two. So we'll start off with the easiest possible, the second easiest possible example. I am not going to take the limit of the constant function. Your book does it, you can look there if you need to review the limit of a constant function. Instead, the second easiest one, I'm going to take the limit as x approaches c of x. What should that be?
C.
C. Good. Let's prove it. Okay. Let's just check. Our function is f of x equals x. Okay, if we're trying to match the definition, that's our function. And f does indeed map from the real numbers, which is the set A, to the real numbers. And the point C really is a cluster point of the set A. Okay. Now, just like with the other kind of limits, let epsilon be given. We have no control over epsilon except it has to be positive. Now, set delta equal to, and here I'm going to leave a blank. We'll come back and fill that in when we know what we need to set delta equal to. Now, it doesn't take much thinking ahead to see what delta should be in this example. But in general, it does. In general, at this stage of the proof, you do not know what you need to set delta equal to. Okay? This is the exception. Okay. And then what would we prove? We would prove if x minus c is less than delta, then we want to prove that f of x minus c, that's the limit we want, which in our case is exactly the same as x minus c, absolute value, is less than epsilon. Okay. Now, that is what we want at the end of the day. Okay. And you can see what we really want is just this little piece on the right. We want x to be within epsilon of c. What we're allowed to control is how close x, well, sorry. Yeah, because this is kind of a silly example. We are allowed to directly control how close x is to c, right? So you can see from this that what we really want to do is we just want to set delta equal to epsilon. And then we can say if the distance between x and c is less than delta, which is equal to epsilon, then indeed the distance between x and c is less than epsilon. Any questions on that?
got a question about assigning delta a value.
Yeah.
So, what what quantities do we have available for assigning? Because obviously we can't use x.
Yeah, that's a great
for
question.
assigning the delta, but can we use c and l?
Yeah. Yeah, so that's a great question. You can use anything but x. Delta cannot depend on x, but it can depend on epsilon, c, l, anything. Okay? The only thing it cannot depend on is x. And in fact, if we go back up to the definition, frequently, you'll write this as, delta of epsilon. As epsilon changes, delta has to change too. But then we're thinking about c and l as constants, so you're always allowed to use those two. Okay. So here it was a function of epsilon. Our next one is going to be a function of epsilon and c. Okay. Okay. So, just a comment before we move on, because I don't want to keep doing this. It is rarely necessary to specify a. Okay. When it is necessary to specify a, we really have to specify it. But when it's not, we just kind of assume, okay, here's a function. I'll let a be. We usually in this semester we just assume a is some open set centered at C. Okay, and it's an open set that's open interval centered at C even, and we just assume that it's a small enough open interval that F doesn't have any points in there that it's not defined at. Okay. For nice enough functions, this is good enough. If your function is nastier, then you do have to specify the domain essentially. Okay, so from now on, I'm not going to specify a unless I have to. So now I'm going to do a second example. Here we go. The limit as x approaches c of x squared is what? I'll take guesses first. Yes, c squared, thank you. Okay. You might object to this example because it's a continuous function, so obviously it's a limit at a point in the domain should be its value there, right? But we haven't talked about continuous functions yet, and in fact that is kind of the definition of continuous functions. So we have to know how to do these limits first. Okay. Our function is f of x equals x squared. Okay. Now, I'm not going to jump right into the proof. If I jumped right into the proof, I'd say let epsilon greater than 0 be given, and then I, find delta. Instead, I'm going to jump straight to the estimation that we need, or the approximation that we need. Okay. So, what do we want to make small? We want to make f of x minus c squared, which is the same thing as x squared minus c squared, small. Specifically less than epsilon, but I'm not going to mention epsilon right now because we haven't set it up. Okay. Now, how are we going to control the size of that? Okay. So what we're going to have control over with our delta is that absolute value of x minus c. So generally, you would like to kind of factor that out. Okay. In this case, it factors out nicely because x squared minus c squared is the difference of squares. So that'll factor as x plus c times x minus c. Okay. And then once I've factored it, I might as well give both terms the absolute value sign. Okay, so this is the absolute value of x plus c times the absolute value of x minus c. Now, that absolute value of x minus c, that is perfect. We are directly allowed to say that's small because we get to choose delta, and delta is an upper bound on how big that is. Okay, so that's great. How do we get a handle on the absolute value of x plus c?
What we can do is setting a condition on the absolute value of x minus c. Also is setting a condition on x, and we can kind of translate that to a condition on x plus c.
Yeah.
And then if we, do some stuff happens.
Yeah, perfect. So c is a constant. We're not scared of c. Generally, at this stage of a limit, you're trying to get rid of all the extra x's, right? And replace them with bounds based on c, okay? So I'm going to take a really simple one. So the whole point is, if we draw a picture, here's c. We're going to be assuming that x is very close to c, okay? And therefore, the absolute value, I'll write a line above this, but the absolute value of x plus c is, by the triangle inequality, it's less than or equal to the absolute value of x plus the absolute value of c. Okay? Well, we're not scared of the absolute value of c, and the absolute value of x will have to be very close to it. Okay. Here's one way to do it. There's a couple ways to do it, but if x is within 1 of c, then that would correspond to having a delta equal to 1, okay? And at the end of our proof, we'll just say, well, we want delta to be always less than 1. So if x is within 1 of c, then the absolute value of x is at most, well, it's less than the absolute value of c plus 1. Okay. So the absolute value of x plus c is most the absolute value of x plus the absolute value of c, which is less than 2 absolute value c plus 1. Now, what have we done? We'll just summarize what we've done. Therefore, so long as x is within 1 of c, the thing we want to make small is less than 2 times the absolute value of c plus 1 times the absolute value of x minus c. Now, if we want this to be less than epsilon, well, then we want two absolute value c plus 1 times absolute value of x minus c less than epsilon, or solving that for how close we want x to be to c. Okay. This is perfect. This is exactly what we want. Okay, we've got a condition on how close x wants to be to c in terms of epsilon, and the absolute value of c, which again is just a constant. We don't care about it. It's not scary. Okay. So now we've done all of our calculation. Let's do the proof. Okay.
Dr. Batter?
Yeah.
How do we know that epsilon over 2 absolute value c plus 1 is less than 1?
That is a good point. We don't. We're going to need to insist on that.
Then wouldn't it not work for all epsilon?
You'll see. Okay? Let epsilon greater than 0 be given. Okay, we're doing the proof now. Let's write that line down. Set delta equal to the minimum of 1 and epsilon over 2 absolute value c plus 1. Okay. Then, if x minus c is less than delta by the above calculations, x squared minus c squared is less than epsilon. I guess I'll add a as desired at the end, because that's what we wanted to show to get the limit thing.
So at the very beginning, you started with absolute value of x minus c is less than 1, I think.
Right. So not well.
So
depends on depends on how we define very beginning. But yeah, right there.
Yeah. So how did you choose 1?
Oh, okay. So in this class, we've got our favorite constants. Our favorite constants are 1. 1 is our number 1 favorite constant, and then our number 2 favorite constant is 1/2. Okay. And you might notice that, right? When we need a stupid bound, we either use 1 or we use 1/2. Usually you use 1/2 when we're cutting something, right? Trying to split the difference, just use 1/2. Okay. Any number would work there, except if you change that 1, then you got to change that 1, and then you got to change that 1, right? Doesn't matter. This could be 7s, right? They could all be 7s. It's fine.
Yeah, I still don't understand how the absolute value of c
x minus c
Yeah,
less
okay.
than 1
I'll tell you what.
would lead us
Yeah.
to.
I'll tell you what. I'll do that in a second. Okay. I want to just finish the overview of the proof first. Okay.
Okay, gotcha.
Okay. So we said if we set delta equal to this is an incredibly common technique where we've got a minimum in there because we want to satisfy 2 conditions or 3 conditions or 4 conditions, right? You put a minimum, then you're guaranteed to satisfy all of them. That minimum is how we get to assume that x is within 1 of c. Okay. And it's also how we get to assume that that x is within epsilon over 2 epsilon value c plus 1 of c. Okay. Okay. So in any kind of a slightly complicated limit, I recommend writing your proof this way. Okay. Let's write down the thing we want to make small. That was x squared minus c squared. Right? And let's estimate it. So we're trying to get an upper bound on it. And we're trying to get an upper bound that has precisely that one little absolute value of x minus c and bound everything else. And then at the very end of your proof, just say, okay, now I'm going to write the proof. Let epsilon be given. Here's delta. By the above, it works. Okay? Now, Thomas had this question about the triangle inequality. I have a more general point about this. I think these absolute values are perhaps scaring some people unnecessarily. Okay? Whenever you see this, so I'm going to make this point. We're going to do a theorem, and then if we have time, we're going to do one more example. Or if we don't have time, I'm going to stick around and do one more example. So I guess I'll be doing one more example anyway. When you see this kind of thing, I do not want you to think that this is this scary absolute value of a difference thing. And, so, okay, if the number is greater than 0, then that's x minus c. If the number is less than 0, then that's minus x plus c. That should not be your first thought, okay? Your first thought should be distance between x and c. The distance between x and c. Okay? So the exact statement was this. Okay. Let's draw a picture. That's the second thing is you should draw a picture. Here's c. Here's c plus 1. Here's c minus 1. Absolute value of x minus c less than 1 means that x is somewhere there. Right? It's within 1 of c. Okay? Now, if we want to translate these, so I said, I can go farther. I can say every time you see an absolute value, that is a distance. On the right-hand side, we have x minus 0. That's the distance between x and 0. And we have c minus 0. That's the distance between c and 0. And we have a plus 1. So the right-hand side says the distance from x to 0 is less than the distance from c to 0 plus 1. Okay? Now we go back to our picture. Where is 0? Well, 0 is either here or it's over here on the right. It's either on the left or the right. Right? Or it's in there. But either way, the point is the distance from x to 0 is at most if you go from 0 to c and then you go one more. Because once you get to c, x is within one distance of c, right? And that's what the triangle inequality is. Right? It says if you want to go from in this case, from 0 to x, then that cannot be farther than if you go from 0 to c and then c to x. So strictly speaking, the triangle inequality I just said, was if you want to go from 0 to x, that cannot be farther than going from 0 to c, and then going from c to x. But that is the same as going from x to c, because distances do that. Doesn't matter which direction you're going.
I see. So it's less c minus x, but more of the distance between. Oh.
Yes, absolute values are always distances, but I can't spend any more time on that today.
Yeah, it's hard
So,
to make sense. Thanks.
Mm-hmm. Good. Okay, so our theorem. Theorem 4.1.8. Let f map from A to R, and suppose C is a cluster point of A. Then it's an if and only if, but I guess I will copy the book here. The following two conditions are equivalent. The first one, I hope you can guess, the limit is equal to L. The second one is going to relate this to our notion of sequential limits, or limits for sequences. If you take a sequence of values of x but the sequence has to be within A, because that's our domain, and it can't be C. You can't have C in there. That converges. If that sequence converges to C, because it's a sequence of x values, then the sequence of values, okay, what's the sequence of values? It's f of xn. That converges to L. Any questions on the statement there?
Could you just explain the sequence being the function? The terms of the sequence?
So we have two sequences here. One is a sequence of kind of x values, and they have to be converging to the point we care about, which is C. The other is the sequence of function values. That's our function evaluated at those.
Okay, thank you.
So the picture we hope to see, if we really are converging, is here's C and here's L, right? And we're looking at a bunch of x values that are converging to C, and we hope to see their function values converging to L. Okay. Now, once we get this theorem proved, then we can apply a bunch of theorems we have for limits of sequences in this context. Okay. I think at best I've got time to prove one of the directions. Would anyone have a preference?
I think one implies two is more interesting. At least I think so.
Okay, let's do it. 1 implies 2. The other direction is in the book. Okay, so we suppose we've got 1. So we know that we got this functional limit. Now, we want to prove 2. 2 says every sequence that converges to C for every sequence, blah, blah, blah. So let us take one of those sequences. So let Xn be a sequence in A minus C that converges to C. Okay. And it wouldn't hurt to write down what we'd like to do. We want to show that the sequence f of xn converges to L. Okay. Again, that's what we would like to show. It's not, I'll highlight it so we don't lose track of it. That is a limit of a sequence. So when we're going to prove a limit of a sequence, we let epsilon be given.
I have a question.
Go ahead.
So this sequence xn in the theorem or in this proof, does that have to be like strictly increasing or strictly decreasing?
No, my picture was a little bit misleading there.
Okay.
Not at all. Not at all. I can jump around.
Okay.
Maybe similar to that question, do we have a theorem that guarantees the existence of that sequence?
Ah, sorry. I really should have pointed this out. Why are there such sequences? Right there. C is a cluster point.
Okay, and then we can just take all of its really close neighbors and make a sequence of those.
Yeah, yeah.
Okay.
Yeah. So a cluster point, you can always approach it with a sequence. Okay. Now we know that the limit as we go to C of f of x is L. That means that there is some delta such that if x is a point of A that is not equal to C and it's within delta of C, then f of x minus L is within epsilon. F of x and L are within epsilon. Okay. That is applying the definition that the limit of f of x is L as x approaches C. Now, what we really want is we want to show that the sequence of function values f of xn converges to L. Well, we know that the xn's are getting close to C. So, because the sequence xn converges to C, there is I can never decide if I should put an A or an an before capital N in N. But there is an N in N such that we're going to be, what do we want these points to do? We want the xn's to satisfy that. We want them to be within delta of C. Okay, so there's an n in N such that xn minus C is less than delta. So, I mean, x is within delta of C for all little n, at least capital N. Therefore, for all little n, at least capital N, we have, and you just track back what the consequence of this is, because xn is within delta of C, f of xn is within epsilon of L. So we have f of xn minus L, absolute value less than epsilon, proving that the sequence f of xn converges to L.
So what we did here was we took the limit definition and swapped the x's for xn's.
Yeah.
Okay.
Yeah, perfect. But we also used the sequential limit definition a bit as well, right there.
So originally you say, you just use the definition of the limit of a function.
Mm-hmm.
So any point on the domain close to the cluster point is, sufficiently close. The function value is close to the limit. So then the corresponding term in the sequence, they're also close enough to the cluster point, even if it's not like a continuous thing. There's terms. And that's why we make that last statement. It's just the way we define the sequences.
Yeah, I mean, really, you said corresponding term in the sequence. You could go farther. You could say corresponding tail of the sequence, right? But yeah, that's the point. Because the function converges. Once we get close enough to C, our function values are close to L. Well, we were given that the sequence gets close to C. So eventually the function values have to get close to L. Okay. For the opposite direction, I thought about this for a little bit. I really do think the book's proof is the best you can do. You have to do a contrapositive. So when we want to prove 2 implies 1, we prove that not 1 implies not 2. Okay. So for that direction, we say, suppose the limit is not equal to L. Okay. Which means that, well, we've already negated the definition of a limit before. then you use that to actually construct a sequence of xn's that do converge to C, but such that the function values do not converge to L. Okay. There's a lot of if you wanted to break this theorem down into like just remove all the definitions, just break it down, replace limit f of x as x approaches C equals L with whatever its definition is, and then, so on and so forth. Let me just point out, this theorem would be a complete mess. You'd have so many quantifiers all over the place because you're proving that some complicated definition that had 3 quantifiers is equivalent to some complicated definition that has like 6. And you're proving this, for all functions and all cluster points of the set. So anyway. Consequences. Okay. If you can find 2 sequences xn and yn that converge to C, would both converge to C, but f of xn, either does not converge okay, sorry, let me change this a little bit. If you can find a sequence, we'll do the one sequence first. xn that does converge to C, but the sequence of function values does not converge, then f of x has no limit at C. Why is that? Well, this is just direct consequence of that theorem we just proved. If f, so we take the contrapositive, if f did have a limit at C, then that sequence xn, because it converges to C, would mean that the sequence of function values has to converge. Okay. So we talked last time about what does it mean to show that a function doesn't have a limit at a point, and I said, well, if you're just using the definition, you have to eliminate all possible real numbers as your limit. Well, this just made your life a lot easier, right? You just have to find some sequence that converges to the point such that the function values don't converge. Okay, that'll do it. Now, the other thing that'll do, if you can find 2 sequences with different limits, 2 sequences, xn and yn that both converge to C, but they have different limits. The function values have different limits. Okay. Let me just point out, if either of those limits that I mentioned here failed to exist, then you would be in the case above that we already talked about, where you have a convergent sequence of x values such that the function values don't converge. So if you can find 2 sequences where they do both, the function values both converge, but they converge to different things, then you're off the hook too. You have no limit there. We did an example at the end of last time where we looked at this sine function that's -1 up to 0, and then it's 1 after 0. And I just mentioned, I said that it has no limit at 0. And then I thought about it and I was like, oh no, we don't have a way to prove that. Well, we do now. Okay? Take two sequences. One is, set xn to be minus 1 over n, and the other one would be yn equals 1 over n. Right? They both converge to 0, but the function values of the minus 1 over n's are all -1, and the function values of the 1 over n's are all 1. So, by the consequence of our theorem, our function cannot have a limit at 0. Okay? So, I've already run a couple minutes over our official time. If you have to go, that's perfectly fine. I'm going to stick around, and I'm going to keep recording while I do one more example of a limit from the definition. Okay, but before I do that, are there any questions?
Well, in this example, you just said, the function values are constant functions, but you use like harmonic sequences as the example. So
Yeah.
not necessarily.
Okay, so we talked about earlier, somebody said, why do you choose 1? And I said, well, 1 is our favorite constant. And we use 1/2 when we can't use 1. And when we want a sequence approaching 0, it's 1 over n.
Okay. So we're just looking for something in this case that converges to 0, but it doesn't have to be. Never mind. It's the function value. Yeah.
So
I just had to think about the definition.
Right, and so in terms of why do we use 1 over n? Well, I mean, try to tell me a simpler sequence that converges to 0.
Yeah, there's nothing, right?
Yeah. So that's why we use it.
And then if this was shifted, you could just have your sequence 1 over n plus c,
Yeah.
and you can just shift it whichever way you want.
I'm always doing that. Yeah, whenever you want a sequence that converges to c from the right, you're going to do c plus 1 over n. So that's why you see so many 1 over n's in our proofs, because when we have a choice and we just need it to converge to 0, we're always going to go 1 over n. Okay.
I have a question.
Yeah.
So in this case, though, xn and yn, both of these sequences converge to 0, and so they have the same limit, right?
The xn's and theyn's have the same limits, yes.
Okay.
But the limits mentioned up here are the limits of the functions.
Uh-huh.
And my function was this sine function, so f of x is 1 if x is positive, 0 if x is 0, and -1 if x is negative.
Okay, gotcha.
So when I'm doing f of xn, I'm getting -1s, just a constant sequence of -1s. And when I do f of yn, I'm getting a constant sequence of 1s. Okay, good. Any other questions before I do this one last example?
For where you say the two limits are not equal to each other, do you have to say that xn, like under the limit, do you have to say xn approaches c?
So we already said, so it's a good question. I'm going to say two things about it, okay? The first is we already said that xn converges to c. Okay. The second thing is, if we put anything under that limit, it would not be that. It would be that n, that's terrible, that n is going to infinity. Because in these two statements, the only thing that's changing is n. The xn's aren't changing; they're fixed.
Right. Okay. Thank you.
You're very welcome. Okay. Last chance for any questions? So this is a final example. It could have gone earlier in the lecture, but I had to get to that theorem. We're going to take the limit of 1 over x as x goes to c, and we're going to show that indeed that is 1 over c. Okay. First of all, is that true? Do you think?
As long as c's not 0.
Yeah. Right, so you have to be a little bit careful.
Makes sense.
Oh. Right. Obvious statements like that, you always want to check. Is everything defined? What is, we know how to do this. What happens when we try and take the limit as x goes to c?
It blows up.
So it does not exist. Because, for example, you take the sequence xn equals 1 over n, then our sequence of function values would actually be the sequence n, which does not converge. Okay. So let me stress this, that in some other contexts which are not this class, you might want to say that thing converges to infinity. We will never say that. Okay, there is no converging to infinity for us. A thing that goes off to infinity always diverges. Okay. This function is 1 over x is an odd function. So it's got some symmetry. So what I'm going to actually do to make our lives easier, I'm going to assume that c is not just not equal to 0. I'm going to assume that it's greater than 0. And then you'll know that because of the symmetry, if c were less than 0, then we would also have this. Okay. You'll see where that matters. Okay. We're going to do proof like the square case. So we want to make, okay. We've done enough examples. So you see f of x is 1 over x. That set A, maybe I should write this out. So we can't let A be all real numbers now. It has to be the biggest we can make it. It's the open interval from 0 to infinity. Okay, because f is not defined at 0. And so we can't have 0 in our set A. And that's kind of why we want to do this condition, because we can only consider one side of 0 at a time. Okay. So we want to make this thing small. Okay. Well, we have. Let's follow our previous recipe. We want to factor out somehow an absolute value of x minus c, a distance between x and c. How would we get a distance between x and c out of this?
We can make them have like denominators, and you get x minus c.
Yeah, let's do common denominators. And now you see, actually, we're inside an absolute value, so we can flip them. Right? And going back to my point earlier, you want to think about absolute values as distances. So, the distance from point A to point B is the same as the distance from point B to point A. And now we see we can pull out a 1 over cx absolute value, and we're left with an x minus c, distance from x to c. That distance is great. That's the thing we get control over. The other thing is not great yet. It's not great yet because we've got to get some control over it. Okay. Now, one over c would be fine. 1 over c is just some constant. But 1 over x is not fine because it's changing. So again, we want to bound the 1 over x in terms of c. How can we do it? So here's 0, and here's c. Any thoughts?
We can use the same trick as before. We can say the absolute value of x is less than the absolute value of c plus 1. Well, we want to say greater than absolute value of c minus 1. So when we flip them, right?
Yeah, let's do this. Let's do this. Okay, so if x is within 1 of c, then the absolute value of x is at most the absolute value of c plus 1. Right? Is that a good bet?
Shouldn't we use that absolute value of x is greater than the absolute value of c minus 1? So
Okay.
when we do the reciprocals, we get what we want?
Yep. That's the direction we want, because we're going to do reciprocals of fractions. Is that good?
I think so.
What if c is equal to 1? Yeah, if we did this, our
I see a
proof.
problem.
Yeah, if we did this, our proof could only be true for c. It could only hold for c greater than 1. Right.
Right.
So there's another trick. Instead of, let's go to our picture actually, and let's see what's going on here. The problem is, oops. The problem is that we might have c minus 1 over here and c plus 1 over there. Okay, if you're too close to 0, we got a problem. Okay, going to our picture though, remember 1 is our favorite constant, but our second favorite constant is 1/2. Okay, but instead of subtracting 1/2, let's split the difference from c to 0. Okay, let's say that x is close enough to c that it's within c over 2 and 3c over 2. Then you can kind of see how the inequality is going to work out fine. So I'm going to change it to that. If x is within c over 2 of c, Then the smallest x could be is c over 2. And the biggest x could be is 3c over 2. Although these are all strict inequalities.
So why exactly are we using c over 2 again?
C over 3 or C over 4 or C over 5 or any of those would be fine. But we tried being within 1 of C and it didn't work. So now we're going to try to split the difference, split the distance between C and 0.
I see. Yeah, I was wondering why you would need c over n, but actually I kind of get it now. Thanks.
Good. Okay, so if this holds, then that holds. So then our upper bound on 1 over cx. Oh, and let me point out, if this is true, then since c is positive, x will have to be positive. So we can drop the absolute values now. And now our upper bound on 1 over cx, trying to bound a fraction. You make a fraction bigger by making the denominator smaller. So we look at the smallest that x could be. And we come over here and we say if x is equal to that, then we'd have 1 over c times c over 2, which is 2 over c squared. Okay. Now, what did we do? We said, yeah, we looked at the quantity that we needed to make small. Yeah, it's equal to that. If x is less than, if x is within c over 2 of c, then that part is bounded by 2 over c squared. So we've shown that if x is within c over 2 of c, then the thing we're interested in, which is equal to, I'll add this step in the middle here, is less than 2 over c squared times the distance between x and c. Okay, now we're going to do the real proof now. Now let epsilon greater than 0 be given. And set delta equal to, let's go over here and we'll do some scratch work. If we want 2 over c squared times x minus c to be less than epsilon, then we want x minus c to be less than 2 epsilon over c squared, I think. I'm an idiot. That's totally wrong. I can't do math anymore today. Epsilon c squared over 2. Better? Okay. Set delta equal to that. By the above calculations, if x minus c is less than delta, then 1 over x minus 1 over c is less than epsilon. As desired.
I have a quick question. I have to go to another class soon. So
Yep.
it's about the condition where, well, also shouldn't we have the minimum of, it'd be the minimum of this value and c over 2 to guarantee the other condition.
Oh, I'm sorry. I totally
And then-
forgot to throw in the
yeah.
minimum. Yep.
And then I don't see how we go from if epsilon c squared over 2 is greater than c over 2, how it still holds. If you could do that really quickly.
If epsilon, sorry, wait, can you say that again?
If epsilon c squared over 2 is greater than c over 2, how does the definition hold when delta is equal to c over 2?
Oh, okay. So let me just do this real quick. Oops. We need to take a minimum of this. I probably didn't want to do it this way. There we go. So we definitely need to take a minimum of the c over 2 and that. Okay, and then you're worried about what happens if the c over 2 is actually the smaller of these?
Yes.
Then when we come up here, we'll still have that this is less than, because c over 2 is actually smaller, this is still less than 2 over c squared times epsilon c squared over 2.
Okay, and then those cancel and you get the epsilon. Okay, I got it. Thank you so much.
Mhm.
Have a nice weekend.
Okay, you too. Okay, and any final questions? And then, yeah, go ahead.
Kind of like the strategy we have here, you want to factor out the x minus c if you can, because we know that it has to be small automatically.
Mm-hmm.
And then whatever problematic part you want to set a bound on,
Mm-hmm.
which you do by looking at the distance between x and 0 most of the time. I'm sure there are other like tricks, but pretty much you just you want to bound the part that you factor out,
Mm-hmm.
so that the whole expression can be bounded in either
Yes.
case.
Yep.
Minimum.
And the thing you get to play with is you get to choose how close x is to c. Okay, that's precisely
that's
what
the
you get to
thing we
choose.
adjust, right? Is that x minus c. Okay.
Yes.